Hello, class. This will be the recorded lectures for Chapter 5, which talks about Introduction to Probability. And I find this to be a challenging part of the statistical curriculum, but a very important one. Every basic stats class has to introduce probability, because when you take data and you do calculations like we do in that percentile and means, et cetera, reason why we do that is to make predictions on what's going to happen with the data set that we have. And so to understand that, the math world introduces this idea of probability. And so let's start with section 5.1, and basically this is the basic introduction. And the three concepts that we're going to be going over is the first three. The idea of sample space, the idea of computing a probability, and then the third, and probably the most important, is given a set of data. What we talk about is the empirical method. Calculate the probability using that set of data. And that's what we do in statistics. So the introduction here is the first, is there's typically an experiment, and the typical experiments that we talk about is flipping a coin or rolling a die or rolling dice. And if we were in class, I would be doing that with you now. It's a little harder with regards to just me here. So we'll talk about the theory, and I'll give you some equations as well. So the idea of probability is the first thing you need to do is to figure out how many possible outcomes there are. And that's a challenge. I think it is a bigger challenge than most people think. And we call that term sample space. And what we mean by sample space is how many possibilities there are. And the best way to think about the sample space is, let's first talk about flipping a coin. That's usually the easiest thing. And so when you flip a coin, there are two possibilities on a single coin. You could get a head or you can get a tail. So if you flip a single coin, the sample size or sample space has two possibilities. How about if you're flipping two coins? Two coins. Well, if you think about it, what are the possibilities? Well, we could have a head and a head and a tail and a head, or two tails. So how many possibilities are in that sample space? There are 4 possible outcomes. What about flipping 3 coins? Some of you might think there's only 6 possibilities. 2 times 3 is 6, but there's actually 8 possibilities. And let me draw that out for you. 3 heads, right? And then head, head, tail, head, tail, head, and tail, head, head. And then we go to head, tail, 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 head, tail, and then tail, tail, head, and then the last one would be 3 tails. So if you count that, there are 3 of them. And so the idea here is that when you calculate the sample space, you need to know what the experiment is and how to do this calculation. And this is called the fundamental counting principle. And it is defined by the number here of the experiments that you do multiple times. So for example, If you did a single flip of a coin, it's 2. If you do 2 coins, it would be 2 times 2, which is 4. If you did 3 coins, you multiply again by 2, which is 8. And again, if you multiply again by 2 for 4 coins, you would see that would be 16 for 4 coins. And you could write those all out. I'll let you do that if you like. So understanding the fundamental counting principle is really important. And I'll when we walk through this lecture, I will talk about calculations of different experiments using this fundamental counting principle. Getting back to the book, in this section, they introduce this idea of sample space with just a single experiment, flipping 1 coin. Here, rolling a die. And we do that quite a bit in probability calculations as well. So there are 6 numbers on a single die, 1, 2, 3, 4, 5, 6. So using the fundamental counting principle, what would be the total sample space of rolling 2 dice? Well, if you do that, it would be 6 times 6, so that would be 36. What would be the total sample size of rolling 3 dice? That would be 6 cubed, or 6 times 6 times 6, and that would be 216. So you see, it starts to get complicated reasonably quickly, especially if the experiment has a lot of outcomes. Here's where statistics comes in, and that's letter C here, where you want to do some sort of survey or something or selection, and you have 10,000 students. So our sample space in this case would be the 10,000 students. So moving on, when you calculate the probability, the idea is it's done via a fraction. And what we mean by that is that the probability values are always going to be a number between 0 and 1. And sometimes we talk about it in percentages. And remember, when you do a percentage of a decimal number, you just multiply it by 100. So sometimes it's talked about 0 to 100%, which is the same as 0 to 1. Seems like this book likes to use decimals, so I will follow that. And the idea that if the probability is 0, that means it cannot occur, impossible. And the probability of 1 means that it's certain going to occur. It's always going to occur. And well, if you get those 2 numbers, it's not very exciting, right? So usually when we do these calculations, there's going to be a number in between. And so here's the formula for the calculation, where you have the number of outcomes in your sample space. And that's typically the number n. And we've used that n in our statistical calculations as well. And what's in the numerator is the number of successful outcomes. And that would be k. And so to do a couple calculations, let's do one right here. And so this one says that if you roll a dice, what's the probability of rolling an odd number? Well, in our sample space, we have 6 possibilities, 1, 2, 3, 4, 5, 6. And from our outcomes, what are the odd outcomes? Let me clear this. And so our sample space, 1, 2, 3, 4, 5, and 6. And the odd outcomes is 1, 3, and 5. So the way to think about that is this is the n value, and that is 6. This is the k value, and that is 3. So the probability of odd, and we use the p for probability, would be 3 over 6 or 1 over 2. Sorry about that. I was looking for the right slide. Here's another example that we'll walk through. And this is more of a probability for this lottery. And this one's kind of a good way to think about it. So what is the probability of if you have a number between 0 and 9,999? So they have 4 digits. So if you ever see those 4 balls pop out when you do the lottery, and so you could have 4 zeros as the smallest number and 9999 as the largest number. So if you count all those numbers up, there would be 10,000 of them. So that is our n value in this case. And if you want to know what's the probability of you having all the same numbers, and so there are 10 of those possibilities. And so let me just write those out for you to make sure that you get that. So one of them is 0, 0, 0, 0, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, 3, 4, 4, 4, 4. So you see there's 5 of those because we're starting at 0, right? Sometimes people might think there's 9. And so that's the classic mistake. Remember, if you start counting at 0, you have to think about adding another number. And if you count that, you see you would have 10. So you would be 10 over 10,000, and that would be 0.001. So most of the time, you talk about probabilities. When I speak in applications, I don't use decimals. I usually use percentage. So this would be 0.1%, because you would multiply this by 100, and you would get 0.1%. I do believe that most of the calculations that you're going to do in ALEKS are asking for decimals in this case. So the other thing that you want to think about, and that's what I have to admit the gambling allure is all about, is this idea of law of large numbers. And if you do something many, many times, what ends up happening is that the theoretical probability will become what you end up getting. And so, for example, here, I have a little table that if you do, say, just tossing 4 coins, and it says you only got 1 head, which if you think about it, what is the probability of getting a head? 1 out of 2, so it should be 50%, right? You see, if we get to 100 here, we're doing 64, which is closer to 50. But you can see if you do 10,000, or if you even did 100,000, you see that number gets much, much closer to 50%. So I guess that's the allure of the lottery, right? I mean, even though the probability of you getting a winning lottery ticket is really low, if it's not 0, right? And so that's the idea. But if they have enough people buying lottery tickets, obviously, the organization or the government that's running the lottery will end up making money. And so that's the theory behind that. And so I'm going to stop the recording on this one, and we're going to continue the probability lecture and finish section 5.1 in the next one.